Okay, section 4 of 5, and it's in this particular lesson we're going to look at the Chinese remainder theorem and how it enables us to solve simultaneous congruences. Now, all right, so I've written up an example here. Solve the following simultaneous congruence. So what we've got are two equations that describe x. So x here has a remainder of 2 when divided by 3, and a remainder of 3 when divided by 5. And so we're looking for the family of solutions for x that where x solves or fits into or satisfies both these conditions. So if we have a look at start to have a look at what x could be. So x is 2 mod 3. So x can be equal to, in 2 mod 3, 2, 5, 8, and so we go on. All these in mod 3 are remainder 2. And so we just keep going down, and so x represents all those possibilities. Now over here, x represents, well, x can be 3. Now we're in mod 5, so x can be 8, x can be, we just go up in 5s, don't we? 13 can be 18, can be 23, can be 28, and the list goes on, and it's an infinite list, it's endless. So what we're after are the family of solutions. Well, we can see some solutions here. I've got 8 here. All right, I've got 8 there, and my next solution, well, I don't seem to have my next solution yet. So if we just keep going, 20, 23, there we go. There's my next solution at 23. Okay. And if we keep just going on a little bit further, so 26, 29, going up in 3s here, all these, remember, have values of 2 in modulo 3. So we keep going, and these have value 3 in modulo 5. So, and we keep going, and there we go. I've got the next one now, and it's 38. Right, so what's happened here is that we've got this difference of 15 that seems to be taking place between solutions. 8 to 23, 8 and 23 to 38 is 15, and the first solution is 8. So it looks to me as if what we've got here as a solution, how do we represent this? So our solution, our x, is equal to 8, 23, 38, etc. Now we know, don't we, so this has got a gap of 15 here, so we're going up by 15 each time. So if I want to represent this in a linear way, I would say my solutions are equal to 15a, but I need to represent that first value there of 8, don't I? So 15a plus 8, would that be right? So that means that when a is 1, I've got 23. When a is 0, I've got 8. When a is 1, I've got 23. When a is 2, I've got 38. That seems to be right. Now, how do I write this in modulo form? Well, I write that as 8 in mod 15. So my x solution here, my solution to this pair of simultaneous congruent statements is that, they are congruent statements, so these need a third line. This is my solution here. Now, I did that manually, just by looking down and by sussing a pattern. Now, the Chinese remainder theorem is going to help us out, and so is actually the linear Diophantine equations that we looked at in a previous unit. Firstly, the modulus becomes 15 from 3 and 5. So if these are co-prime, then the Chinese remainder theorem tells us that our solution will be just the product of those two. So in fact, we can write the Chinese remainder theorem. Right, the Chinese remainder theorem tells us that if M1 and M2 are co-prime, then the simultaneous congruences congruences, simultaneous congruences, right, where x is congruent to A mod M1, and also x is congruent to B mod M2, right, then if that's the case, then the simultaneous congruences, I don't need to write then, have a unique solution in modulo M1 M2, or it will look like this. It'll look like C mod M1 M2, so the product of them. So that's the Chinese remainder theorem. Right, let's block that off. Right, that's what it says, and it just tells us that our when we're solving simultaneously, that our modulus will be the product, as long as they're co-prime, of M1 M2, and we found that out there. Now then the key then becomes how to find 8, or how to find C. So how to find C. So C can be found manually. Now manually, if the numbers are small enough, or using Diophantine equations. Diophantine equations. Okay, so we found that manually. Now we could then therefore have a look at how to do it, or find it using Diophantine equations. Okay, so now just let's look at how to find C, or this value here, using Diophantine. Now, Diophantine equations. We didn't need, here the numbers are so small that we can very quickly get to 8 just by listing, and it really is 8. This is our first common value, our first simultaneous solution. It represents this number here, and then from that point onwards, we're in step with the lowest common multiple, or just the product of 3 and 5 as their co-prime. That's the lowest common multiple. So it's really just finding that first value. Now, I would suggest using manually when the numbers are small, Diophantine equations for when the numbers are larger. So we'll just make that note here. Best used for large numbers. Now we don't have large numbers here, but I'll just use it because it just ties up nicely with what we've just done, and we can see that we'll get 8 using them. And it's also just a bit of a recap on how to use them. So what we're looking to do here is that we've got two equations. X equals, now 2 mod 3 looks like that, and 3 mod 5 looks like this. This is remainder 2 when divided by 3. So x is equal to some multiple of 3 with a remainder of 2, and the other equation is x being some multiple of 5 with a remainder of 3. So from there we can say that, well, 3a plus 2 must equal 5b plus 3, and therefore 3a minus 5b must equal 1. Okay, now Diophantine equations, remember, look for integer solutions to equations. Now we can find them if the greatest common divisor of our 3 and 5 is equal to this value here of 1. So in this case, our GCD of 3, 5 is equal to 1, so we're okay. And now we just need to use the if we were going to use Diophantine algorithm, or it's not the Diophantine algorithm, it's the Euclidean algorithm. In order to solve the Diophantine equations, the Euclidean algorithm would suggest this is a good recap also. Euclidean algorithm All right, it goes like this. We take 5 and we write it as 3 plus 2. And then we take 3 and we write that as, well, it's just 1 lot of 2 plus 1. And then we take 2, we write that as 2 lots of 1, remainder of 0. Now remember, the last non-zero is our remainder, sorry, our greatest common divisor, and in this case that matches with what we know there. But in order to then rewrite 1, we just go backwards from this. So we write, okay, because my solution, my 3a minus 5b is equal to 1, so I write 1 as, well, I write it as 1 equals 3 minus 2, which is all good. Remember, I want them in 3s and 5s, so that 2 is going to be rewritten as 5 minus 3. It's a trivial example, isn't it? So it's 3 minus 5 plus 3. So what we've got are 2 lots of 3 minus 1 lot of 5. Right. So well, it's actually the other way around. It's 3 lots of just so because it's 3a, so it's 3. We've got 2 lots of 3. And I've got 1 lot of 5. So in that way, A is equal to 2 and B is equal to 1. And therefore, with those values of A and B, I can put back in up here, and I can find out that X is equal to, if A is equal to 2, then putting A equals 2 in there, I get X is equal to 3 by 2, which is 6 plus 2, which is 8. And I'll also get it from here, putting B equals 1 in there. I'll get the same result, X equals 8. There's my simultaneous equation being checked out at X equals 8. So there's my value of C. So I could therefore say that my solution is that X is equal to 8 mod 5 times 3, which is 15. Okay, shall we do an example? Just having a look here, we can go to exercise 5D, and what I'll do is I'll again get you to pause the video. We'll do 5D. Let's do question 1A, 1AI, but we might do, we won't need to use the Euclidean algorithm for that, or the Diophantine, so we will do that, but we'll also then go down and perhaps use, so that'll be question 1A, and then we'll go and do question 2, just having a look at the numbers. Perhaps we'll do 2AI as well. So if you pause the video now, pause, to struggle to spell pause there, and then come back and check your solutions in a moment. Okay, so let's go and do these questions now. So this first one, we are looking for X equals 3 mod 5 and X equals 4 mod 7. Okay, right, let's look for our values of X here are going to be 3, then 8, then 13. Our values of X here are going to be 4, then 11. So now going up in 7s, and we're going up in 7s, we're going up in 5s, pardon me, going up in 5s. So we go to 18 and 23 and 28 and 33. And in 7s, 32. Have we come across any commons yet? Yes, we have, 18 and 18. So our solution is going to be X is equal to 18 mod. Now, because 5 and 7 are coprime, and it's just 18 mod 35. Okay, actually we're not going to do, 2A part 1 I don't like, because I think it just is a trivial example with both remainder 6. So I'm going to actually change that to part 2, which we will do now. If you haven't done part 2, pause and proceed after you've completed the solution to it. So this is 2A part 2. which says that x is equal to 6 mod 13, and that x is also equal to 3 mod 22. Is that the one I'm doing? Yep, 3 mod 22. So remainder 3 when divided by 22, remainder 6 when divided by 13. Okay, now in this case we're not going to run this manually. It'll take too long. I know that 13 and 22 have a GCD, they're coprime, so I know my resulting mod will be 13 times 22, and 13, so my resulting mod, so 13 times 22 is equal to 11 times 13, which is 143, double it is 286. So my mod is going to be 286. What I need to know is where my first solution is. So what I'm going to find here is I'm going to find out where I'm going to take these and write them as equations. So this is x is equal to 13a plus 6, and this one here is x is equal to 22b plus 3, and I'm going to solve them simultaneously. So I get from that 13a plus 6 is equal to 22b plus 3. So I get 13a minus 22b is equal to minus 3. Now minus 3 is a multiple of the GCD of 13 and 22. GCD of 13 and minus 22 is 1, so I can multiply that straight up. So that's no problem. So what I'm going to do is I'm going to solve for, right, I'm going to solve for 13a minus 22b equals 1, because that's the GCD of 13 and 22. Then I'm going to multiply that through by minus 3 to get what I need. So how do I do that? Righto, off we go. I say that 22 is equal to 13 plus 9. Excuse me. I say that 13 is equal to 9 plus 4. I say that 9 is equal to 2 lots of 4 plus 1. And then I say that 4 is equal to 4 lots of 1 plus 0. So that's my solution. I then backtrack and say that 1 is equal to 9 minus 2 lots of 4. I then say that 9 is equal to 22 minus 13, and my 4, 2 lots of 13 minus 9. So I just simplify that a bit. Minus 2 lots of 13 plus 2 lots of 9. 22 and 13, I need to get there, so they're okay. 22 and 13, they're the numbers I need. All right, remember I'm aiming for these numbers. I've got 2 lots of 13 here, so I'm happy with that. It's the 9 I need to change into 22 minus 13. So I end up with 22 minus 13 minus 2 lots of 13 plus 2 lots of 22 minus 2 lots of 13. So I end up with, counting them all up, 22 plus 2 lots of 22, so that's 3 lots of 22. I've got minus 13 minus 2 lots of 13, so that's minus 3 lots of 13 minus 2, so that's minus 5 lots of 13. So from that, to get 1, my solution to this equation here, 13 lots of minus 5, so therefore A is equal to minus 5, 13 lots of minus 5, minus 22 lots of B, so that's 3, so B is equal to minus 3. So just check that. 13 lots of minus 5, minus 22 lots of minus 3, that's minus 65 plus 66, so that equals 1. Alright, so that's what I need, but I want minus 3, don't I, as my solution up here. If we have a look, this is what I'm solving for right here. So I want for minus 3, I've got for 1, so I'm just going to multiply by minus 3. So 13 lots of 15 minus 22 lots of 9, that's going to equal minus 3. 13 lots of 15, so there's my A. Alright, so let's get this right. My A is equal to 15. And my B is equal to, you can see my minus 22 lots of B is equal to 9, and that gets me my 3. So when A is 15 and B is 9, I've got my solutions. When A is 15, x is equal to 13 times 15 plus 6, which is equal to 13 times 15. 10 15s are 150. Add another 3 of those, 195, that's 201. Check it through this solution. B is equal to 9, so 22 times 9, which is 198 plus 3, which equals 201. So that checks out. So that's my value of C. So my solution, therefore, is x is equal to 201 mod 286. Okay, go ahead and do the rest of exercise 5D, and then go to the 5th and last lesson in this unit on modular arithmetic.